Thank you, everybody, for being here, both in person and virtually. It seems to be prophetic that a lot of our people are online out in space somewhere. So I think I'm funny. No one else does. So I'm Chris Hyrcyna. I am the Dean of the School of Physical Sciences, and I want to really thank everyone for being here. I know some of you come from far away, Hawaii, Orange County, whichever is your home. Thank you for being here today. It's a really special event as we get to officially launch the new Department of Astronomy and Astrophysics that was just really christened not but a year ago, or this is our first real year. Let me tell you a little bit about the School of Physical Sciences, which it's housed in. We are about well over 200 faculty now, and we have some very large individual departments. We have chemistry and biochemistry, we have physics, we have astrophysics and astronomy, and we have mathematics. So it's a very wide, sort of diverse group, but we're one of the things that pulls us all together is this idea of emergence of life, and where that really fits in with the astronomy and astrophysics department is it's sort of beautiful to see the whole school come together on that point. You know, these are some of the founding departments of UCSD, so we take a lot of pride in that. 65 years later, nearly all of the undergrads that come to UCSD take a course in the School of Physical Sciences. So we probably teach 70,000 students a year within our school itself. So not only do we have some of the most excellent researchers who are so incredibly well funded, we also teach some of the most of anybody on campus. So we're kind of a unicorn in the School of Physical Sciences. We do everything really well. And that's a testament to the faculty we have here. So why did we create this new department? Well, we really wanted to highlight the amazing work that's been done by these faculty, and also to put us on the map amongst other high-quality institutions across the country. We want to recruit the best researchers doing the most innovative, cutting-edge work, as you'll hear about today. And the department started with 12 faculty, and then last year we hired 6 new faculty, 3 of whom you'll hear from today. So I couldn't be more proud of being able to bring in this amazing cohort of young and exuberant talent, as you'll see very soon. So you're going to hear a lot today about, are we alone? What's the universe made out of? What's the purpose of life? Is there life elsewhere, right? So stay tuned for those exciting questions. Not only are some of these people the best researchers, but they're also the best teachers and mentors. So we have a thriving undergraduate program that they have created, and we also are very proud of being very accessible to transfer students and bringing them into the fold after their first 2 years elsewhere, and being able to come in and finish up their degree here. So there's lots of things happening, and you'll hear a lot of that from our new inaugural chair, Alison Coil, who is the Ingrid and Joseph W. Hibben Chair in Space Science and Education. So again, one of our esteemed faculty who are not only a great researcher, but also a great teacher. Alison is an observational astrophysicist studying how galaxies evolve with cosmic time and how they're influenced by large-scale structure of the universe. So with that, I'll let Alison introduce the rest of the program. So thank you for being here.
Okay. Thank you all so much. It is wonderful to see all of you. Some of you I know, and some of you I don't yet, but I should. So I'm going to tell you a little bit about why we created a new department. So 2 years ago, we were approved by campus to establish a new department of astronomy and astrophysics. That is not the same thing as having a department. And we have spent the last 2 years designing and building it from the ground up. So I wanted to provide, before we hear about some of the research, some of the context and motivation for why we created the new department. So The University of California is a world leader in astronomy. Astronomy, we like to say, is a jewel in the crown of the entire UC system. The University of California owns and operates the Lick Observatory near San Jose and also the twin Keck telescopes in Hawaii on the summit of Mauna Kea. The Keck Observatory in particular, sorry, that's on the upper left is Lick and on the upper right are the twin Keck telescopes. The Keck Observatory leads all ground-based observatories, so that means on the surface of the Earth as opposed to satellites in space, worldwide in terms of metrics of research productivity and impact of publications. So what I'm saying is that we have access here at UC to the best telescopes in the world. UC faculty across the UC system are also leaders in the current and next generation, both ground-based facilities such as the Simmons Observatory on the lower left, Vera Rubin Observatory, which is being built in Chile, and also space-based satellites such as the James Webb Space Telescope, JWST, in the middle there. And then on the right, the upcoming satellite called the Compton Spectrometer and Imager, or COSI, which is a high-energy gamma-ray NASA mission that's being led by Professor Stephen Boggs in our department. So there, across the UC system, there are nearly 100 astronomy faculty in UC. That represents nearly 15% of astrophysics faculty in the nation. So UC really leads the country in astronomy and astrophysics, and it just makes sense for us to capitalize on that here on our campus. The new department builds on a long and rich history of astronomy here at UC San Diego. So the Center for Astrophysics and Space Sciences was a research unit that was founded here on campus in 1979. And it was established in part to support developing satellites and instruments for NASA missions, such as one of the original instruments on the Hubble Space Telescope, HST, as well as an instrument on the upper left there, and then on the upper right, an instrument for a high-energy X-ray satellite called RXTE. And then UCSD was also the home for pioneering women in the field, including Sally Ride, who you've probably heard of, on the lower left, the first American woman astronaut. And then you may have heard of Margaret Burbidge on the lower right. She is a professor here who helped discover how fusion in stars leads to the creation of the elements in the universe and also the elements in you. She was a luminary in the field. She was very active, particularly in the 50s and 60s when there weren't very many women in astronomy. So here on this campus, we are really standing on the shoulders of giants in creating this department. Also, astrophysics research is strongly supported nationally. So the US spends $2.5 billion annually on astronomy and astrophysics research and facilities. That comes from NSF, National Science Foundation, NASA, and DOE, Department of Energy. And then there's additional one-time investments, large investments on the scale of like 1 to 10 billion for individual new telescopes and satellites, such as the James Webb Space Telescope and the Vera Rubin Observatory, which you can see on the upper left there. And for example, the upcoming Nancy Grace Roman Telescope. The top universities, as the dean was saying, in the country also have astronomy departments. So the majority of top-ranked R1, meaning research universities, have astronomy departments, including 3/4 of the Ivy League schools. So establishing an astrophysics and astronomy department here on this campus really places UC San Diego in this upper echelon of research universities in the country. There's also, this is the only graph I'm going to show you on the right. And you don't have to read the axes. It's time on the bottom, and it's number of degrees on the y-axis. There's a strong and growing interest in degrees in astronomy and astrophysics, both at the undergraduate and graduate level. So this is showing undergraduate degrees. In the last 20 years, nationally, there's been almost 3 times as many degrees in astronomy and astrophysics in the last 20 years, and the demand at the graduate level has increased by about double on that same time scale. So there's a lot of interest from students. Another motivation, I love this picture, another motivation in creating the department was to allow us to broaden the research scope of astronomy here on campus. So as the dean was saying, last year we hired 6 new faculty, which is just astonishing, as we started with 12, so that's a 50% growth. That's unheard of for an academic department to grow that much in a single year. And it was because we established the new department and we had this very strong support from campus, from our executive vice chancellor and our dean, that we were able to hire so many faculty in 1 year. And in doing that, it allowed us to both strengthen research in areas that we had already established on campus, such as exoplanets, which is studying solar systems that are around stars other than our sun, and cosmology, all the way from exoplanets to cosmology. And cosmology is the study of the universe on the very largest scales. And then it also allowed us to expand into new research areas where we didn't have faculty working in them. So that includes planetary science, the study of objects in our solar system, and you'll hear about that in a little bit. We expanded into the transient universe, exploding stars and supernovae, and also gravitational waves, and you'll hear about that as well. So we were able to hire in these new areas and bring new research to campus that didn't exist before. What this image is, I could just stare at this for hours. This is real. It's not an artist rendition. This is a JWST image of a nearby galaxy called the Phantom Galaxy. And one of our faculty, Karen Sandstrom, has been studying this data set and other nearby galaxies as part of what's called the FANGS survey. Astronomers are very good at naming things. So this is, this is real. We also, another major motivation in creating the department was to create a new undergraduate program. So it's currently in its first year of existence. We've established 2 new majors and a new minor, and we, and by we I mean the faculty, not me, have been developing a host of new courses this year, and we'll have some new courses next year as well. Both general education, courses for non-majors, there's just a few examples: astronomy and science fiction, which is being taught for the first time this quarter, and climate change and astronomy, which will be taught in the fall, the astronomy of climate change. And then also upper division courses for majors on things like quantum mechanics and astrophysics, the fluid dynamics of astrophysics, data science and astronomy, thermal astrophysics. I know you're all very excited to take those courses. Those are for majors. When we created this new curriculum, particularly the upper division courses, the faculty realized that this was the program that we all wished we had taken, that had existed when we were undergraduates. I can't tell you how exciting it is to sit down and write out what you always known should have existed but didn't. It's a very modern curriculum, and it's designed to support students in a variety of careers, whether they go into grad school or they go into industry. Students can go into science communication, science policy, data analysis, data science, all kinds of quantitative careers. I don't know how widely known or appreciated this is, but there are former astrophysicists littered throughout Silicon Valley, for example. A lot of data science and astronomy and astrophysics. So the undergraduate program, we're just ending our first year. We also transferred a relatively recent, so it's 3 years old, PhD graduate program in astronomy to the new department. The program has about 15 students currently, because it's 3 years in existence. It takes students roughly 6 years to earn a PhD, and so it'll grow over the coming years. And so the students complete graduate level coursework and then work very closely with an advisor to learn how to conduct and lead independent research. It's through the students that much of the research in the department happens. And it's a really incredible opportunity for graduate students to get to lead a PhD thesis using data, for example, from the Keck Observatory or JWST, or use data from the San Diego Supercomputer Center. And lastly, I wanted to mention that the department leads a variety of outreach and public engagement events across the greater San Diego area. So this includes visiting K-12 schools with a portable planetarium, doing community events such as Astronomy on Tap. If you haven't heard of this, this is at local breweries where we answer astronomy questions from the public. And we work closely with the Fleet Science Center in Balboa Park. Those are just a few examples. Doing this kind of outreach and community engagement, I think, is a real win-win. It gets us academics out of our offices and away from our laptops, talking to folks in the community. And of course, it's really exciting and engaging for people in the community to hear about the latest research and just get to talk to professional astronomers and understand what that career path looks like. So I want to leave you with this amazing image that a UC San Diego alum took of star trails over Geisel Library. So pointing north towards Polaris, the North Star. We in the department absolutely love this image. We are so thrilled that it was taken by an alum whose name is on the slide. And we display this prominently in our building and in the dean's office. So I know you want to hear about the research in the department, so I'm going to now introduce Professor Shelley Wright, who has agreed to MC the rest of the program. So Shelley has been a really key contributor in building the new department and helping to develop, in particular, the PhD program and also recruit our new faculty last year. Shelley's an experimental and observational astrophysicist who specializes in optical and infrared instrumentation, galaxy formation and evolution, and the search for extraterrestrial intelligence. So please welcome Shelley.
Thank you so much, Allison. It's really thrilling to be here to see the launch of the new department. I've been told that our executive vice chancellor, Elizabeth Simmons, has arrived, and I think we'll be hearing from EVC Simmons at this point before we go to the research section. So please welcome EVC Simmons to the podium.
Thanks so much. I apologize for being late. I was doing a review of another department, and once you're in those, you can't leave until the external committee is kind of satisfied. But I really wanted to be here with you today just to say briefly how very proud I am of my colleagues in astronomy and astrophysics for having the courage and the inventiveness to dream up being a new department all of their own. As some of you may know, I am a member of the Department of Physics, the original home department, and I think it's wonderful that we now have also a Department of Astronomy and Astrophysics, because the UC as a whole has been a leader in astronomy since and astrophysics since the 19th century, and UC San Diego since its founding in, there are various debates about was it 1960, was it 1961, but the physics department was 1962, and it included astronomy and astrophysics from the beginning. So given all the long history of who the amazing faculty in astronomy and astrophysics have been, which I won't take you through all that because I don't want to make the program later, but given the incredible history of who has been a part of this department and the Nobel Prize-winning work and the other groundbreaking work that they have done, this is just so appropriate, and it makes me very proud. I am currently a particle physicist, but I started actually doing work in astrophysics back when I was an undergraduate and a graduate student. And lately, I have come back towards working on some projects related to dark matter. So I feel a special kinship with this department, and it really makes me very personally glad to be here as part of this celebration today. So thank you very much, and I'm looking forward to hearing all about the great research in the next presentations.
All right. Okay, so tonight we are going to hear, is it tonight already? It feels like, I'm an astronomer, I feel like it's always night. We're going to hear about the icy, cold, mysterious moons in the outer solar system, followed by enigmatic black holes, and then the invisible matter, dark matter, that binds all the galaxies together. Did I get that? They might have gotten the... So first, let me introduce Assistant Professor Samantha Trumbo, who will talk to us about ocean worlds in our own backyard. Samantha studies the surfaces, atmospheres, and potential habitability of these bodies in our outer solar system using ground and space-based telescopes and data from the spacecraft that gets to visit closely to these bodies. And I'd also like to point out that Samantha Trumbo is an alumni to the Scripps Institute of Oceanography. So please join me in welcoming Professor Samantha Trumbo to the podium.
All right. Thank you so much for that introduction. I'm really excited to be here today and be able to tell you a little bit about my favorite planetary bodies and how we study them. But I want to start really quick with some motivation on why we study them. So I think we can all agree that the possibility of life elsewhere in the universe is one of our biggest questions. And it's also one that has really risen to the forefront of astronomy today with the thousands of extrasolar planets that have been discovered around other stars. Many of them on orbits that could enable surface liquid water like we have on Earth to exist. And of course, we know that liquid water is key to life as we know it. And so the discovery of these very distant planets is really exciting for that prospect of life beyond Earth. But in parallel to that, we have also been finding new reservoirs of liquid water much, much closer to home within our own solar system, with the realization that many of the moons of the giant planets in the outer solar system actually harbor global internal oceans of liquid water locked beneath very cold, icy surfaces. And if these moons could be habitable, then not only would that kind of change our perspective on what it means to be a habitable world, but it would also mean that there are possible abodes for life within reach, right in our own backyard that we can go explore. So what I'm showing you here is just a selection of the icy moons of Jupiter and Saturn for which we have the best evidence of subsurface oceans. And you can see right off the bat that these are not like boring balls of ice and rock, right? They're really diverse. They're different sizes. They have different surfaces, interiors. Saturn's very large moon Titan has a really thick atmosphere, while its very tiny moon Enceladus is actively erupting plumes of water vapor into space from its south pole. But the most important thing that you can see from this diagram is that our solar system is actually teeming with liquid water, right? So I want to take the example of Jupiter's moon Europa, which is just about the size of Earth's moon, of our own moon. But we think it probably has about twice as much liquid water as all of Earth's oceans combined. So if we want to follow the water in terms of understanding habitability beyond Earth, then these ocean worlds like Europa are really, really important places to explore. And we know from looking at Earth that life can thrive in really extreme environments, like the hydrothermal vents that we find at the very deepest parts of our own oceans. And so the idea is that maybe life could find a way in the very kind of alien environments of these outer solar system moons as well. But in order to understand that, we really have to understand the composition and the chemistry of these oceans and how they have changed over time. And that is a super difficult problem because we can't study them directly. And we have to look at what we can see instead, which is their overlying surfaces and atmospheres, which provide records of how these worlds formed, how they evolved, and what they are like today. So these are the questions that my research group and I are very interested in answering. And there are sort of three key sources that we use to try to answer these questions and learn about the chemistry of these places. The first are planetary exploration missions like Galileo or Cassini, which actually travel to these worlds and provide us with very up-close images, spectra, in some cases in situ measurements. And the second are telescope observations, which, even though we obtain them all the way from Earth, actually provide us with richer spectral detail and a wider spectral context that helps us differentiate between different chemistries. And then finally, we really need laboratory experiments that simulate the materials and the conditions of these places and really help us interpret our observations in the context of planetary processes. And so I want to just show you a brief example of these three different directions working in harmony to teach us something new about Europa, which is that moon of Jupiter with just about twice as much liquid water as Earth. So the Galileo mission to Jupiter showed us that Europa's surface is just totally covered in really fascinating geologic features where the ice is fractured and it's broken apart, and material from below has made its way to the surface, where it appears discolored relative to the background ice. And then laboratory work done up at the Jet Propulsion Laboratory showed us that something really interesting happens to salts, like sodium chloride, basic table salt, which you're seeing here, when that salt is subjected to electron radiation, which we know Europa is constantly bathed in thanks to its location within Jupiter's very intense magnetosphere. When irradiated, that salt actually changes color due to the growth of defects in the crystal structures that absorb at very specific wavelengths of light. So then, motivated by this, what our team did was we used the Hubble Space Telescope to look for these spectral absorption signatures of irradiated salt on the surface of Europa. And we found that its discolored geologic terrain actually does contain sodium chloride. And that's what you're seeing illustrated here in this plot of Europa's surface reflectance versus wavelength as seen by Hubble and compared to laboratory data of irradiated sodium chloride, which fits the data quite well and implies that something very familiar, right, table salt, the most common salt in Earth's oceans, resides as well in material sourced from Europa's interior, and by extension probably resides in its internal ocean. Most recently, we have been using observations with the James Webb Space Telescope to build on this result, so far finding carbon dioxide, which is another familiar component of Earth's waters within those same geologic terrains on the surface. And what you can see from this plot of Europa's near-infrared reflectance from James Webb is that this is really chemically and spectrally rich data that now allows us to do things like search for other salts on the surface and understand the presence of molecules like hydrogen peroxide, which you might also be familiar with from your own medicine cabinets, and which also allows us to now probe the very tenuous atmosphere of Europa for things like water vapor. So it's a very exciting time, and it will also really complement the future spacecraft exploration of this ocean world, which is now very imminently on the horizon with the recent launch of NASA's Europa Clipper mission, whose overarching goal is to understand the potential habitability of Europa. I'm super fortunate to be involved with this mission, and I had the great pleasure of attending the launch myself at the Kennedy Space Center in Florida. By far, one of the most exciting moments of my life. I can't even tell you. But I am even more excited for when we eventually get to Europa, because we are going to be able to do so much cool science. And so I just want to take a minute to give you a quick preview of what that is actually going to look like by showing you this animated flyby of Europa, one of about 50 that we have planned. And you can see a bunch of different colors in this animation. Each time you see a color, that is a different remote sensing instrument taking data. Blue flashes are the camera snapping pictures. Orange is the thermal instrument looking for hotspots. Purple and red are the ultraviolet and infrared spectrometers. And you can see that as we reach closest approach and really zoom past, all of those instruments turn on at once. And at the same time, Clipper is collecting actual samples of atmospheric gases and dust, and it's measuring the gravity and magnetic fields, and it's using radar to probe the local ice shell structure to really build up what we hope will be a very complete picture of this potentially habitable world. And I'd just like to end by saying that I hope and I think that Clipper is really going to lead us into what will be an era of ocean world exploration, where both with planetary missions and with ever improving Earth-based observatories, we can really start to better understand where we fit in a solar system that we're learning has abundant liquid water. So thank you so much.
Wow, thank you, Samantha. That gives ocean exploration a whole new meaning, especially thinking about beyond Earth in the future. The next person who would give us a talk is Assistant Professor Ethan Nadler, who will talk to us about small galaxies packed with dark matter. Ethan's research focuses on galaxy formation, dark matter, near-field cosmology. And I'd like to point out that Ethan recently launched a program called AstroReach SD, which involves San Diego high school students to learn how to do computer science and data science to help study a lot of the things we're hearing about in astrophysics. So it's a local program connected with our department. So please join me in welcoming Assistant Professor Ethan Nadler.
All right, thank you so much for having me. I'm so excited to tell you about the smallest galaxies in the universe and how they might hold the key to understanding the nature of dark matter. So I'd like to start here. This image shows the Blanco telescope, which is in the mountains of Chile. And above the telescope at the top left, you see something that's probably familiar to you. This is our own Milky Way galaxy. So you're looking at stars and gas in the disk of the Milky Way. And the Milky Way is a fairly typical galaxy. It has billions and billions of stars, so there are many other galaxies in the universe like the Milky Way. But in this image, you can also see two smaller galaxies. These are the Large and Small Magellanic Clouds. They're only visible from the southern hemisphere. And they're much smaller than the Milky Way. So the Large Magellanic Cloud is about 1/10 the size of the Milky Way, and the Small Magellanic Cloud is even tinier still. Now, the remarkable discovery that we've made is that this visible light that's coming at us from these galaxies is really only the tip of the iceberg. And in fact, most of the matter in our universe is an unknown substance that we call dark matter. So 85% of all of the matter that there is in the universe is fundamentally unknown to us. And that means everything we're familiar with, everything that makes up galaxies and stars and planets and you and me is only about 15% of everything there is. Now, I want to come back to this image and imagine that we could put on dark matter glasses. What if we could see the dark matter that's actually underlying this visible light coming at us? And it would look something like this. Now, this isn't a real image. This is a prediction from a supercomputer simulation that I'll tell you about later in the talk. For now, all you need to know is that the brighter regions in this image have more dark matter. The dimmer regions have less dark matter. And you can see that the dark matter is most concentrated exactly where the visible light was coming from our own galaxy and from the Large and Small Magellanic Clouds. But there are also lots of smaller clumps of dark matter predicted by this simulation, and that's what I'll be talking about in the context of small galaxies today. Now, the first point I really want to drive home is that dark matter drives the formation of structure in the universe. So without dark matter, those galaxies that I was telling you about never would have formed. We wouldn't be here to ask the question of what dark matter is. So if we want to understand the emergence of life, which we heard is a major theme driving the research in our department, then we better understand dark matter itself. Now, much of the pioneering work on dark matter was done by Vera Rubin in the 1970s. And what Rubin did was conduct very detailed observations of spiral galaxies, for example, our neighbor galaxy, Andromeda. And Rubin measured the rotational velocity of stars and gas as they orbit around the centers of these galaxies, and found something very interesting. So the rotational velocity of the stars and the gas actually kept increasing the farther out from the center of the galaxy Rubin measured, even beyond the visible extent of a galaxy like Andromeda. So this was early but very compelling evidence that there was much more gravitating mass in these systems than the visible light accounted for. In Andromeda, there was about 10 times more dark matter than visible matter. And in recent years, we've actually made very detailed measurements along similar lines in our own galaxy, the Milky Way. This image shows you a measurement actually from the Gaia Space Telescope. So it's composed of billions of individual stars. And Gaia measured the motions of these stars in great detail and found a similar story. The Milky Way is also dominated by dark matter. So I'd like to come back to the simulation that I mentioned earlier and show you how we think the dark matter underlying the Milky Way actually formed. This is an example of a simulation that I developed with my group at the San Diego Supercomputer Center. What you're going to see is the dark matter structure underlying the Milky Way form. So as the movie plays, it will zoom in, hopefully. There we go. 1 second. I think it might just be slow. It will zoom in on the Milky Way as its dark matter forms. So if you focus on the center of the screen, the first thing that you'll see are some major collisions. The Milky Way underwent early major mergers with other galaxies, which built up its dark matter content. And at the end of the movie, you'll see smaller clumps of dark matter falling into the Milky Way. And these, in fact, are chosen to exactly resemble the large and small Magellanic Clouds that I was showing you at the beginning. So we now have this picture that the smaller galaxies orbiting the Milky Way came in with their own clumps of dark matter. This has also been observationally confirmed, so measurements of the Magellanic Clouds show that they are also dominated by dark matter. Now, it gets even more interesting if we think about smaller galaxies, and it turns out that the Milky Way is surrounded by an entire host of tiny galaxies that are absolutely packed full of dark matter. So if we take one of the simulations that I showed you before and zoom in even farther, the dark matter structure looks like this. Again, the brighter regions have more dark matter, the dimmer regions have less dark matter. So the Milky Way would live at the center of this big clump of dark matter, but you see that there are many other tiny clumps of dark matter orbiting around the Milky Way, and these we expect would host their own galaxies that are correspondingly smaller. So understanding this connection between the properties of these dark matter clumps and the properties of the galaxies that they host is a major research area in our department. Now, amazingly, this prediction has also been observationally confirmed. So in the last 2 decades, we've learned that the Milky Way is surrounded by about 60 dark matter-dominated, what we call dwarf satellite galaxies. And I want to show you an example of one of these systems because it's really very different than anything we had seen before. So this image, it shows what otherwise looks like an unremarkable part of the sky. There are some bright stars, some galaxies, but you couldn't pick out a tiny galaxy by eye necessarily. And in fact, astronomers have developed very detailed search algorithms to actually find which stars in images like this are associated with a particular galaxy. So I'll help you out. I'll circle the stars that are part of this galaxy. This particular galaxy is called Segue 1. And in fact, it's the smallest galaxy that we have ever discovered. It has about 300 stars, unlike the billions of stars that the Milky Way has. But at the same time, it has about 300 million stars worth of dark matter in mass. In other words, there's about 1 million times more dark matter in Segue 1 than there is visible matter. So excitingly, there's a new generation of telescopes that's coming online, actually starting this year, that we expect will discover hundreds of these dwarf galaxies, greatly increasing the number that we know of. And so we think that this might help us understand what the fundamental nature of dark matter is. Now, one of the telescopes that will be part of this kind of data revolution is very fittingly named the VR-Rubin Observatory after Rubin's pioneering work in the field. And it's now fully constructed in Chile. It's actually measured its first photons coming from the sky. And the first data from Rubin is coming at the end of 2025. The reason it's so powerful is that it has a 3.2 gigapixel camera. That's the largest digital camera that humanity has ever built. And it will survey half of the sky, basically the entire southern hemisphere, about once a week. So UC San Diego is a key member of the Galaxy Survey that Rubin will conduct, which is called the Legacy Survey of Space and Time, or LSST. And so we're really excited here in the department to start analyzing this data as soon as it comes in. Here's an example of the kind of transformation that Rubin will make. This is a particular region of the sky imaged kind of at our current capabilities using the Sloan Digital Sky Survey. It's focused on a particular galaxy, but you also see some background galaxies and some bright stars in the foreground. Now, if we take this same region of the sky, but image it at the depth that Rubin will achieve, the structure of the universe really pops out. So the central galaxy is resolved in great detail. Many faint background galaxies that weren't visible at our current resolution come into view. And in fact, some of those bright foreground stars are completely saturated because Rubin is so sensitive. So tools like Rubin are really incredible for studying the faint universe. And as I said, we're super excited to analyze this data as soon as it comes in. Now, the note I want to end on is how these observations might actually tell us about the fundamental particle physics nature of dark matter. So I didn't tell you this before, but all of the simulations that I showed you so far assume a certain kind of dark matter, which we call cold dark matter. Basically, this means that dark matter is really boring. It only gravitates, and that's the only force it experiences. And as a result, it clumps very efficiently. So you'll see in the left-hand simulation prediction, there are lots of small clumps of dark matter, and therefore lots of small galaxies predicted. But that's by no means the only assumption we could have made. So the right-hand simulation shows you a different kind of dark matter, which we call warm dark matter. And in those models, the individual dark matter particles are much lighter. So fewer of those small clumps form, and we predict fewer galaxies. So this data that's coming from Rubin is going to provide an experimental test of these hypotheses, different models of dark matter, and will allow us to differentiate between the two. So I just want to end here and leave you with this picture of the dark matter sky. Hopefully I've convinced you that there's lots of interesting discoveries to be made, even though we can only see the visible light. So thank you so much.
Thank you, Ethan. That gives Google Glasses a whole new name. I've been thinking about our dark matter glasses as we progress forward. Now we'll hear from Assistant Professor Floor Broekgaarden, who will talk about black hole paleontology. Floor's work spans data science, statistics, astrophysics to study the formations, life, and explosive deaths of the most massive stars. In her first year, Floor has already led a campus-wide collaborative initiative that's interdisciplinary. It's appropriately called SMASH, which helps researchers both in the data science, artificial intelligence, machine learning, statistics, and the astrophysics and the physics community come together to answer some of the most pressing questions. So please join me in welcoming Assistant Professor Floor Broekgaarden.
Thank you. Yes, and please join our initiative if you want to. So for me and my students, massive stars are actually the dinosaurs of our universe. Because similarly to how paleontologists can use fossils to study how dinosaurs once formed and lived, my group, as astronomers, we use the fossils of massive stars, black holes, to actually understand how these massive stars once formed, lived, and died. That's a lot, so let's unpack that for you. So compared to our sun that's shown here, these stars that I talk about, our massive stars, are 10 to 200 times the mass of our own sun. And they play a pivotal role in shaping our universe through all these different processes. For example, they actually produced all the oxygen that we're breathing in this room today. Something that was led as a discovery by this paper by no other as first author than our own Margaret Burbridge, who moved from the UK here to the US to really discover new novel methods to study stars and shaped really this astronomy in UC San Diego, which eventually transformed in this department that we're celebrating today. So a huge inspiration. Despite the importance of these massive stars, there's actually very little that we know about them. And this is because they're extremely rare. So only 1 in 1,000 stars is formed as a massive star. And they also live fast and die young, with lifetimes that are like 1,000 times shorter than that of our own sun. And when you combine these two, it means that these massive stars are extremely rare among stellar populations in our galaxies today. And this makes it really challenging to study them in much detail in our own Milky Way, where we rely on really expensive surveys. But it basically becomes impossible to study them in detail in more distant galaxies, as these stars are too far away to be resolved individually. And so despite that our universe has like so many stars, more stars than grains of salt here on Earth, Actually, if we think about how many of these massive stars can we study and understand and use to test these models, such as the ones by Margaret Burbridge, there's actually only a few hundred that we can really use. A few hundred, it's nothing. And even worse, these 100 were all born very recently, in the past few million years. Otherwise, they would have already been dead by now and been in a black hole. And so this is really crazy, right? There's really this big gap of stars in the past, massive stars in the past, that we have no observation for whatsoever. It would be as if you're like trying to study like Homo sapiens and like the history of Homo sapiens, but you're only like looking at like a quick picture of like the 100 people in this room today. It's just really difficult. Now, the nice thing is that actually my research group, we think we might have like a revolutionary new way to actually probe this area of massive stars in the past. And this is through what I call black hole paleontology. So using black holes as fossils to study stars in the past. So how does that work? Okay. My favorite thing about massive stars is that now we know as of 20 years that they are usually formed in pairs in a binary. So they have a companion. And life in a pair can be drastically different from that of a single star. These stars can actually interact, exchange mass. And these massive stars, at the end of their life, they actually explode. The outer layer explodes in a supernovae. But the inner part can implode and form a denser and denser object and eventually form a black hole. And so these massive stars and these pairs, if they can survive all these different phases and stay together, which is very rare, they can actually end up forming two black holes, like each one of them explodes, which would look maybe something like this. This is my little visualization. And so these black holes can actually spiral in over billions and billions of years and eventually collide, forming a slightly more massive black hole. Excitingly, this can happen all around us in our universe, where these black holes, as they're colliding, produce these waves in space-time itself, predicted by Einstein about 100 years ago. And these waves, they travel with the speed of light through our space for millions of years, until they eventually reach us here on Earth, where they slightly squeeze and scribble like our Earth itself. Here, it's a bit exaggerated. You wouldn't actually feel it. It's smaller than like an atom size. But in the US, we have built these detectors, laser interferometers like LIGO, here built in the US, that can actually pick up these tiny, tiny, tiny wiggles in space and infer its signal. And the signal looks something like this. This is a chirp, so over time it goes like whoop, slightly up in frequency. And that's like a signal that two black holes have collided. And from these chirps, scientists can actually infer properties of the black hole collisions and the black holes, like their masses or how often they occur. Now, if you love stars, this is awesome. And there's especially one thing that's really awesome about them. And for that, we kind of take a small picture slice of our universe, only a small part. And think about this as like the early universe is like all the way to the left, and the Earth today is like all the way to the right. So we're looking back in time. And the amazing thing is that maybe these massive stars, they form a pair of black holes in just a few million years, extremely fast because they live so fast. These black holes can actually kind of like go around each other for many billions and billions and billions of years and only collide much further in the future, like today. And so this means that the black hole collisions that we're seeing today, even the ones nearby us, actually probe massive stars all the way to the first star formation in our universe. And so this made people like me very, very excited, right? Because that might mean that maybe we can use these black hole collisions that we're now seeing as of 2015, which was awarded the Nobel Prize in 2017. Maybe we can use these black hole collisions actually as fossils to understand and study how these stars formed in the past. And so this is a completely new frontier in astrophysics that's only possible as of 10 years now. And it's something that I've come to call black hole paleontology. So we're really using these fossils of black holes to understand how these massive stars once formed, lived, and died. The challenge, big key challenge of this field, is that when we look at these black hole fossils, we're actually not directly probing the properties of the stars. We're not directly observing the stars itself. So in practice, you really have to forward model how stars evolve and what kind of black holes they leave behind. So you can maybe compare this with how maybe paleontologists, when they look at a fossil, they don't know whether a dinosaur had feathers, but they can forward model dinosaurs with and without feathers and see whether it leaves behind different fossils. Okay, so this is where my group comes in. So with students here at UC San Diego, we use new techniques from AI and machine learning and data science in combination with astrophysics to actually model and build these forward models, these forward simulations of massive stars, to actually open up this new frontier of black hole paleontology. And fortunately, I don't have to do this alone. There's actually some of the students are in this room right now, so you should definitely ask them some questions afterwards. But I have a whole team of students ranging all the way from like mathematics, like the engineering department, data science, AI, physics, and astrophysics, and tons of like collaborators here who are helping me out build this. And I would love to like show you 3 examples of some of the projects that we're doing. So the first project that my students are leading is that we're actually building these forward models like from scratch. And so you can kind of see this as little factories where maybe you throw in like different hypothetical pairs of stars with, for instance, different masses. And then you have this whole factory that models how these stars evolve, which ones explode, and whether they leave behind like a black hole collision. Here shown as like a little black marble. And so these factories are really like what's underlying these forward models. And so it's part, here at UC San Diego, we're part of this like international collaboration called COMPASS that's making and developing these codes. And actually students here at UC San Diego and in my group, they're really helping develop these codes, test these codes, and implement new physics and improve them. And one of the things I'm most proud of is actually one of the things we have really worked on really hard for this code is that we try to make it very accessible. So we actually really reduced some of the computational speed, making it possible to actually run this code on your own laptop, and provided all this documentation and online tools so that students, even undergrads, and even some of my high school students who have continued onwards to win some like national prizes and awards at science competitions, can download this code and just run it on their laptop and do cool astrophysics with it, like simulate their own black holes. And actually, fun fact, you even can go to this website called GW Landscape, pick your favorite pair of stars, maybe decide on like what their metallicity and so is, and then click a button that will actually run our actual code that like our students are working on like right now in our lab. And so it runs this like Compass code, like it shows you the version, and actually will create for you these like animation and interactive like data visualization tools that anyone around the world can use to actually learn and understand some of our science that we're actually doing and contributing to. One of the things I love is that this also means that when our undergraduate students contribute to this code, like people worldwide will use their updates and will be using like their implementation of the code, which I think is so cool. A second really cool project is something that's led by one of my students, NLM. And what she did is that she actually looked at this factory with one of the challenges that most people only look at like what goes in and then look at like what goes out, but they don't really understand or know what's going on inside the simulation. And so NLM is a student who took on this challenge and decided to build a visualization tool from data visualization to figure out, like, okay, if you start with lots of thousands of these stars, can we quantify and understand and visualize what fraction of stars you're losing at each of these different stages of their evolution? And so it can quantify in some kind of like Drake equation framework, but what small fraction of stars you're left behind that actually make it all the way to like a black hole collision, which is so cool. And so, okay, her real visualization tools look something like this, and it's actually super interactive. And people worldwide are now using this to actually understand their data and study these simulations. And NLM just accepted a PhD position in Columbia, where she will be starting this fall. One other thing that I'm very, very excited about is that actually here at UC San Diego, I'm collaborating with like my students, Alex, for instance, and Adam are collaborating with experts from like the physics and AI departments here on campus. And what we're doing is we're taking AI models that have been applied to particle physics experiments to detect rare events in particle detectors and build these simulations that can approximate these like functions and learn these functions along the way, but then instead apply it to these like little factories, these like forward simulations that we have. And by doing so and updating their AI models, we could actually improve our simulation speed by a factor 1,000, which maybe doesn't sound like a lot, but it's a lot. It means that like our simulations that before took like an entire year to complete now can be done in just a few hours, which is like huge. And so with all these tools in hand, my group is really building these new tools to allow us to do this forward modeling of populations of stars and being able to compare them to these black hole collisions, and therefore really open this new frontier and lead this new frontier of black hole paleontology. And it's an extremely great time to be doing this because it turns out in the past 10 years, we've gone from like 3 to 10 to today 100 of these black hole collisions that we have observed today with LIGO gravitational wave detectors. But actually very soon, we're going to go to this new era where we're going to have hundreds of thousands of these black hole collisions detected each year. It's crazy. We're going to see every black hole that's colliding in the entire universe, like each year. It's completely crazy. And this means that if we go back to this picture, that maybe today, with just light, so by just looking at stars, you can maybe see about like 100 of these massive stars and study them in detail. But using black hole paleontology, we can actually really fill this gap. But already today, we have access to like hundreds of massive stars in the past through like the 100 of black hole collisions that we see today. But I'm mostly excited really about this future, where we're going to go to like hundreds of thousands of massive stars in the past that we can study using black hole paleontology and the tools that we develop here. And so this will be really a unique way to study these massive stars and understand the important role that they play in all these different processes in our universe. And it's been so exciting actually to do this here in UC San Diego, where we have all these like resources, both in like computing, AI, data science, but especially astrophysics and physics. And one thing that I really love is like every day that I walk into my office, I actually pass by this like portrait next to my office. And it's a portrait of the Milky Way. But actually, if you zoom in, you'll see that it's signed by no other than the Margaret Bertridge, which I think is so excited and just like super inspires me. And it always makes me wonder like what Margaret like would think if she had known like how we can study her massive stars using like black hole paleontology today. And so I'm so proud to basically continue the legacy of UC San Diego to study massive stars and use completely new tools to like do this with now using like AI and machine learning, which is like such an honor since it's like the department where Margaret really built from scratch. And similarly to her, like also make this trajectory where I started in Europe and like the Netherlands, but then 6 years ago, like moved here and actually really 8 months ago started and for the first time like moved to California, which has been so amazing, honestly. But to be honest, I'm most proud of like all the students here in San Diego that I get to interact with, like through teaching, through the machine learning initiatives like the hackathon we organized for 200 students here, and through my research group that like is really amazing. Like these students, it's so like rewarding to like see them grow into like the leadership positions, both in like industry and academia, and learn all these tools, get excited about them, and then apply them in other applications. So, you know, it's only been 9 months, at least for me here in California, but I think we already learned so much thanks to the help of these students, and I'm just so excited to see what's next for us. So, thank you.
Thank you, Floor. Black hole paleontology is such a poetic and striking way to describe how we're studying the universe with some of the public's favorite topic, which is black hole. And it's great to see how much student interaction there is already within the department. At this time, I would like to invite our panelists to these comfy-looking chairs right here in the front of the room. And I would like to invite the audience for questions about their research, about the vision and the direction of the new department, and anything you would like to ask about the universe. We have people with microphones, and you just need to raise your hand and they'll get you. I see a hand right here for, give me good. Yep.
Thank you. Professor Coil, in some of the images you showed at the very beginning of your introduction, very colorful images, very dense looking. Is that what a person would see? Like if you could be there with that image filled your field of view and you were in a spacesuit or something? Or is that, you need a special telescope with, you have to integrate for 3 hours? I know JWST works in the infrared, which people can't see at all. But for the ones in the visible, I mean, sometimes you see calendar pictures with this because they're so striking.
Yeah, good question. So I think you're referring to most of the images I showed were from JWST, James Webb Space Telescope. The exposure times That's a good question. I actually don't know off the top of my head, and Karen's not here to answer that question. They're not particularly long. No, it's not 30 hours. So James Webb Space Telescope is the successor to Hubble Space Telescope. So Hubble works in the optical. So with your eyes, if you were able to travel to these galaxies, you would see roughly what you see with HST images. JWST, you're right, is infrared. But sometimes, so what I study, for example, is very distant galaxies. So the light, when it's emitted, might be optical, and then it stretches by the time it makes it to Earth. So we see it as infrared, but if you could actually travel to the galaxy, you would see optical light as well. But when we didn't really show this, but when you can look at the exact same galaxy at completely different wavelengths and see entirely different things. So when you think of a galaxy, you're probably thinking of the stars. That's generally what I'm thinking of. That's optical light. But if you look at different, like radio, you can see the gas, different wavelengths, you could see different like temperatures of gas, you could see high energy gamma rays, you could see we can't do this, but we'd be really cool if you could see the dark matter. So this is partly why we have a whole array of different kinds of telescopes and satellites, is because they work at different wavelengths, and so that gives us different views into the different kinds of physical processes in the exact same galaxy. But mostly those were JWST images that were like, I don't know, not even an hour maybe.
Okay. I think we have thank you for all the hands.
Thank you very much. I have two general questions. First of all, if you could sit here in 50 years from now, which of the problems of astronomy or the issues would be solved by then? What the new problems would be? And when do you think you could have a Department of Astronomy at the University of Titan or Europa?
Well, that's a great question for all of us. Maybe we'll ask the chair to answer for the department, and then we can maybe get a quick answer from all the speakers.
Yeah, I actually want to hear from you all about what are the big questions going to be. I mean, I'll just say we didn't talk about dark energy. So if you ever want to freak out our dean, you just talk about dark matter, and you talk about how there's dark matter in this room right now, and you can just see her have this little existential crisis. And then you move on to dark energy, which we really don't even know what that is. So I'm guessing that might still be an open question, but I want to hear from you all.
I mean, my emphasis is a little bit more on habitability. So I think, in 50 years, we're going to know a lot more about what types of habitable environments really exist out there beyond Earth. I really hope that we understand one of these other oceans in our solar system to the point where we can say, could like an Earth-like organism thrive there? Maybe we'll actually get to explore one of those oceans in the future. I don't know about 50 years, but, I can dream.
I guess I could speak a little bit to the dark matter and dark energy problems. Dark matter, the problem has been with us for actually 100 years, so the observations go back even farther than I showed you. So it's a very grandiose problem, and I don't think we can confidently say we'll solve that. But there are the reason it's so exciting, I think, there are concrete things we can learn about galaxy formation in the context of dark matter. So for example, what is the smallest galaxy that ever formed in the universe? I think that's a question we can answer maybe even this decade, certainly within 50 years. Dark energy is challenging for other reasons, but there are new measurements coming from surveys of large-scale structure. So unlike the very small scales that I showed you, much larger regions of the universe that are already giving us maybe interesting hints that dark energy is not quite as simple as we thought it was.
Yeah, I think those are great. I would add also that I think actually in a few more years, we might be able to answer, for instance, questions like, where is all the gold that we have here on Earth? Like, where was it created? Currently, it's still an open question. So we think it might be created from these massive stars, that some of them might form not black holes, but neutron stars. And when they collide, that's actually where all the gold that we see today on Earth comes from. And I would love to see more observations of those neutron star mergers, which might help us answer this question.
Maybe on this side.
We have one more question on this side. Let's go. We'll just go.
Kind of tag team maybe a little bit. I know there was some hand up over here before. Yeah, then we'll go over there.
Okay.
Well, first of all, thank you very much for your dedication, excitement, and presentation to this group. Speaking of earth-shattering news, I want to ask your opinion of the Majorana 1 Microsoft chip, quantum chip that supposedly discovered regularities in the message from the Voyager 1 that contained prime numbers, geometric shapes, etc. First of all, I mean, maybe each one of you could say, do you believe it? And then what are the not implications, of course, those would be gigantic. What are the subsequent steps in verification of the validity of those deductions?
Do you want me to take this question, or? I do research field in the search for extraterrestrial intelligence and thinking about communications and artifacts even within our solar system. I only briefly saw that release, so I think for myself, I would need to know more information about that. And one of the leading things for looking for intelligent communication is looking for things that would show something mathematically or something where nature wouldn't produce it. My response to that question is I think we'd have to look more into it, and I don't know if my colleagues want to say anything more to that.
I completely agree with what Shelley said. Yeah, I would have to know more information to evaluate it myself, but I really think, these big claims require a lot of evidence, so.
Thank you. I'm happy to talk about that afterwards. Other questions? I think in the front row here, and then we have one.
Thank you very much. This was a very exciting presentations that you gave us today. I was wondering, are you interested in water that's on our own moon? Because that's water that was discovered by Ames Research Center, and we're going to need that water to explore the rest of our solar system.
Sure, yeah. I mean, I think that's absolutely a very interesting topic to study. I think the origin, history, and water content of the moon is absolutely something that we should understand. We can do relatively low-cost missions to explore the moon. It's really close by, so I think that's a very exciting question for future lunar-specific missions. Absolutely.
Thank you. And just one other short question. You have so many wonderful graduate students. How are you going to support them over these years?
Chair Alison Coil.
Excellent question. So generally speaking, on the whole, our students are supported in the first year as graduate student TAs. So they help teach our undergraduate courses. And then after the first year, they get into a research group and they work with one of the faculty. And they're typically supported by grants. Most of our grants come from NSF and NASA. So the future there is really unclear. I feel like we're at a really point in time of like maximum uncertainty right now. I think even 6 months from now, we'll have a much clearer answer to that question because the congressional budget will come out. We don't know what it looks like right now. So typically it's through grants, and astronomy has been really well supported in the past. Right now, there's a lot of uncertainty. Yeah, it's a really good question. It's obviously something that's top of mind at the moment.
Yes, right here.
I'm Mike McCabe. I'm a community member. I'm not associated with astronomical study or research, but how do you detect water and other substances inside of the moons of the distant planets?
That's a really great question. So in the case of Europa, that was actually detected via magnetic induction. So the Galileo spacecraft really carefully was measuring magnetic signals near Europa, and it was measuring Jupiter's magnetic field. And what it detected was an induced magnetic field, which implied a conducting layer beneath the surface of Europa. Based on its bulk composition, its density, what we know about the formation of these icy moons, the most logical conclusion for what that conducting layer, near surface layer would be is salty liquid water. We can also build models of their interior structures and evolution that support the idea that you would have oceans on some of these larger, icier satellites. But in the case of the most compelling detections, it's often from this magnetic induction signal.
Is there a question up here?
Yeah, I have two reasonably quick questions, I think. For Professor Nadler, is there perhaps a plan to do something like the Hubble Deep Field experiment with the JWST that might give you insight on dark matter, dark energy?
Absolutely. Actually, JWST is doing that. So it's discovered lots of really early galaxies in the history of the universe that have already told us about dark matter and galaxy formation. The difference with those galaxies is because they're so far away, they're brighter than the ones that I was showing you. Those are the only ones that JWST can see so far back in the universe. But it's already happening, and we're already using that to learn about how galaxies form inside of the dark matter clumps.
All right, and for Professor Broekgaarden, black hole paleontology, the standard punchline for the physics joke is you assume a spherical chicken. So what you have in the gravity wave experiments is you have a oscillating decay of the collapse of the binary pairs of black holes. What parameters can you get out of that tell you how these are different than sort of a classic, regular, spherical, uniform, homogeneous black holes colliding with one another?
Yeah, that's a great question. So, and I would actually maybe say like it's even broader, right? So what these laser interferometers, these gravitational wave detectors are measuring is really like there's two arms, 4-kilometer arms, and they shoot a laser, and they use that, the speed of light is constant. And so if there's no wave, these lasers that are being shot in like one direction and one in the other direction and then reflected back in mirrors, they should arrive at exactly the same time if there's no wave. But then if a wave passes by, it will actually distort and change the length of one of the arms a little bit, a tiny bit, by like less than an atom size, actually. And that's actually what they measure, and it's really, really challenging to do this. It's kind of similar that if you have the largest lake in the United States, that you're trying to get one bottle of water out of that lake and try to measure the differences in height of the lake, just based on getting one bottle of water out. It's extremely, extremely challenging. And so what is nice is that these black hole collisions, they leave a very specific imprint. So as the black holes come closer and closer, the frequency should go up. And so this chirp that I was showing has like a very, very specific like way that it behaves in frequency and in amplitude that we can predict using like general relativity and actually Einstein's theories. And so that's what they're searching for. You can still have that actually, maybe if a tree falls next to the detector or an earthquake happens, it would also distort a little bit the space between these mirrors, right? And so actually these detectors are like the most sensitive seismology detectors. One of them is near Seattle when Taylor Swift was having a concert there. And you know how like people were jumping and they said like, oh, it caused like a little earthquake? This was actually first detected in a LIGO detector that's about like 20 miles away from Seattle and actually picked up this signal through seismology. And so the trick is that we have two detectors. So there's one in Seattle, one in Louisiana. And if there's a truly cosmological signal, it should show up first in one and then in the other. We can actually predict exactly what the time difference should be. And so this is how we know whether it was a Taylor Swift concert or a black hole collision, which is very useful. Yeah.
Okay, I was told we have one question coming from online. So I think this will be for Professor Nadler. The question online was, they've heard recently that there is some theories out there that suggest that dark matter does not exist. And what would that be? What would that be implications to? Are there alternative kind of physics in that discussion?
Yeah, it's an excellent question. Honestly, we're not very happy that we have to posit that dark matter exists. It's a very uncomfortable position to be in. But the alternative that we got everything else wrong about our understanding of gravity and the other laws of physics would be much more troubling. So in particular, theories that, for example, modify how gravity behaves, those are very difficult to reconcile with data we have about the universe over its entire lifetime. So we know both how dark matter is behaving in galaxies today, but also how, for example, the cosmic microwave background formed, which is kind of like a snapshot of the early universe. And the only simple explanation we have that explains all of that data is that there's some other kinds of particles out there, which is what we call dark matter. Modified gravity, although it can explain one or the other in certain circumstances, really struggles to explain both at the same time.
we have one question up here, yes?
Yeah, I have two actually. The first one is, have there been any new discoveries in astrophysics? And my second question is, if black holes, is it possible for them to collide, and can they travel across the universe?
This is
Great. Yeah, well, we'll start with the black hole question first.
This is a great question. I'm like, can I hire you in my lab for the summer? These are exactly the kind of questions that you should be asking. And yeah, indeed. So actually these black holes can collide, and we actually think that the collision product is just like a more massive black holes, and that these black holes might be like wandering throughout space. And they might even collide another time with maybe another black hole if there's enough of these black holes in a certain situation. So there's actually people who are trying to look for this, and especially, for instance, to see okay, if multiple of these collisions can happen, maybe this is the way that very massive black holes can actually form, which maybe are the seeds of these supermassive black holes in big galaxies. So it's definitely super exciting to think about that, and we need to improve our models in order to test those theories. For new discoveries, I got really excited when we saw in 2017 two of these neutron stars collide for the very first time. And not only did we see the collision with gravitational waves, but we actually could also see the light that it produced, and even maybe detect some of the gold by following up these detections with electromagnetic telescopes. So this is, for instance, what Professor Griffin Hosenzadeh is doing here in our department. And it's really, really exciting that this new type of seeing objects with multiple telescopes, so gravitational waves, which is a completely new way to look at the universe, but then also lights. And then we also have people studying neutrinos. It will really open up new discovery space, I think, in astrophysics.
I'm going to build on your fantastic first question, and I'm going to end today's panel by asking Ethan and Samantha and Alison what is your most favorite discovery in astrophysics most recently? So no pressure, but let's...
All
Ethan?
right, I'll start with so to go back to your question, there's discoveries every week in astronomy. Astronomy is done worldwide. And I don't know how to do these alerts on phones and stuff, but you can do a news alert for astronomy stories, and you can get something every single week. Astronomy is not a huge field, but in terms of the number of people, but in terms of the number of discoveries, it's incredible. And there's just more and more data. I hope that was one of the things you all took away. There's enormous amounts of data coming really soon, so there's just going to be more and more. There is something happening right now with dark energy that's unclear. It's not a discovery yet, but there's what's called a tension. Different kinds of data aren't fitting together with the current model in a way that at first I was like, oh, somebody's just doing something wrong. And then the tension has gotten stronger over time to where I now feel tension. I'm feel tension about it. I'm like, something's off. So something is starting to feel very off about dark energy, which is scary and exciting at the same time. And it might take a few years to figure out, or longer to figure out how that gets resolved. But the upcoming surveys are exactly what we need to study it. So there should be a lot coming out in the next few years on that.
So I'm going to interpret your mention of recent as within the last 10, 15 years. So I think the most astounding discovery to me in recent years, and we've been learning more and more about this place as a result of this discovery, but I think the discovery of the plumes of Enceladus is fantastic. We did not know that this moon of Saturn was erupting water into space until the Cassini spacecraft actually got there and saw it up close and discovered these plumes. And then it was able to do the most amazing thing in its extended mission, which was design trajectories that enabled it to fly through the plume and actually collect samples of this extra terrestrial water that's coming from another ocean. Just fantastic. It found salts, it found organics. The most recent Planetary Science Decadal Survey listed a future mission to Enceladus to explore the chemistry of that ocean. What is its plume telling us about its habitability as a top priority? And I'm really excited for the future of that. And that discovery is just always going to blow my mind.
So I'll give a bit of a fun one. It's the same theme I've been talking about, but actually a few years ago, there was a very low surface brightness galaxy survey, and they discovered some galaxies that don't have any dark matter in them. And I actually thought that was absolutely beautiful, because when we make these models of dark matter, this is exactly what we predict, that different galaxies have different amounts of dark matter, and in fact, some of them have lost all of it. So going back to the earlier question about modified gravity, if the visible matter were somehow explaining all of this weird behavior that we see, then those galaxies that lack dark matter shouldn't be possible, essentially. So I thought it was a really beautiful kind of proof by contradiction, in a sense, that dark matter does exist.
Great. Well, let's thank our panelists. But honestly, more importantly, I want to thank the audience for fantastic questions. So thank you. We got to keep our professors on their toes. At this time, I will excuse our panelist. No, for closing remarks, I would like to invite back the chair of our department, Alison Coil, to give us the final words here. Thank you.
Well, thank you all so much for being here today. I hope you take away how much an exciting time this is for the faculty, for the students, for Discovery. The launch of the department is not just an announcement. It's really the beginning of something that's very lasting and we hope impactful on our campus and for the community at large. And we hope that you're walking away inspired by some of the research that you heard about and the talent that you saw on display shaping the department. From ocean worlds in our solar system to galaxies rich with dark matter to how black holes form. It's bold, it's ambitious, and we've shown you just a little bit of the research that's happening in the department. And what makes this even more unique is that we're building it from the ground up. That doesn't often happen at a major research university, that you get to form a new department. And we were so fortunate to bring on 6 outstanding faculty last year, helping us build a really strong foundation for the future of the department. And we're building, as you heard, not just with people, but with incredible tools. So UC San Diego is one of the very few campuses in the entire country that has a supercomputer center on site. That's a game changer for the kind of modeling that you heard about from Ethan and Floor. For modeling various kinds of physical processes over different scales in the universe. And it's another reason that this department is really uniquely positioned to lead the kind of work that you heard about today. And I know from many of our alums on campus that we've heard how they wished that a department like this existed when they were students here. So now your own child or somebody you know or mentor can be part of the new and growing department. So we're shaping education, not just for this century, but beyond. And of course, shaping something new means that we have greater needs. So we need access to telescopes, resources for research support and student support. And the discoveries of tomorrow depend on what we're building right now, today. And science funding, of course, is more critical now than ever. Continued investment in science funding and including in funding for astronomy and astrophysics, it's not just something that's beneficial, it's really essential for this country. It drives innovation, strengthens national security, and fuels economic growth. And without it, we risk stagnation in our knowledge and in progress. So a commitment to science and to astronomy is really a commitment to a more sustainable future for all of us. So if you would like to be part of this journey of the new department, please come find me at the reception. I would be really happy to talk to you. We have several faculty here from the department, not just those who were speaking today, but others in the audience who I know would love to talk to you all as well. And if you didn't get a chance to ask a question, or if you just want to have a more informal conversation or talk more, we have an upcoming virtual department coffee chat on May 19th at 10 in the morning online with the dean and myself. It's a great way to keep the conversation going, talk more about the research in the department, the mysteries of the universe. We can talk about aliens because I know people want to talk about aliens in a low-key setting. And you may already have gotten a postcard, but we will be sending reminders shortly. You can also scan the QR code on the screen right there. We'd love to have you all join us for that. So thank you again for being part of this launch of the new department. Your support and curiosity is what helps propel us towards the next big discoveries. So at this stage, we want to invite you to join us outside for a reception. Thank you so much.